Special relativity. The reflection of light by a moving mirror. We assume a ray of light traveling from point P'1 to point P'2 in frame K'. At time T'1 relative to K', a light ray is emitted from point P'1. At the point of emission P1, we apply the spacetime transformation. At time T'2, a light ray is received at point P'2. For observer K, the point of light emission is point P1, and for observer K', the point of light wave emission is P'1. Applying spacetime transformation at point P2. The difference in time and space intervals between the event at point P1 and P2 are the following. Relative to observer K, θ12 is the angle of incidence. Relative to observer K', θ12' is the angle of incidence. Since the speed of light is constant relative to any observer, observer K say that the distance traveled by the wave on x-axis is x2 minus x1 equals c times t2 minus t1 times cosine θ12. This is equation 3. Observer K' say that the distance traveled by the wave on x-axis is x2' minus x1' equals c times t2' minus t1' times cosine θ12'. This is equation 4. We end up with the following set of independent equations. We can solve them to obtain the relation between the angle of incidence for observer K and K'. We will solve these equations to obtain the intervals x2 minus x1 and t2 minus t1. Substituting x2 minus x1 from equation 3 into equation 1. We obtain the following. Solving for the interval x2' minus x1'. Substituting x2' minus x1' from equation 5 into equation 2. We obtain the following. Solving for t2 minus t1. Solving equation 3 for t2 minus t1. Substituting t2 minus t1 from equation 7 into equation 2, we obtain the following. Solving equation 1 for t2' minus t1'. We obtain. Substituting equation 9 into equation 8. We obtain. Solving for the interval x2 minus x1. To find the relation between θ12 and θ12'. We substitute equation 11 into equation 10, and we obtain the following. Or. Finally we arrive at the formula which connects the angle of incidence in frame K' with the angle of incidence in frame K. If we use equation 4 with equation 1 and equation 2 to find x2 minus x1 and t2 minus t1, we will find the relation between the time interval in terms of the angle of incidence θ12' in frame K', and the difference in space will be. To find the relation between θ12 and θ12', we substitute equation 15 into equation 11. We obtain the following. We arrive at the formula connecting the angle of incidence in frame K' with the angle of incidence in frame K. Or. We assume the ray of light, which is received by a mirror at P2', is reflected at time T2' in frame K'. According to observer K', the angle of incidence and reflection are equal to each other because the event are taking place originally in frame K'. θ13' equals θ12'. According to observer K, the angle of incidence and reflection are different from each other. Theta 13 is not equal to theta 12 prime. At time t2, the ray of light is reflected, at time t3, the light ray is received. Applying spacetime transformation at point P3. According to K prime, the angle of reflection theta 13 prime can be computed as x3 prime minus x2 prime equals negative c times t3 prime minus t2 prime times cosine theta 13 prime. Notice that the negative sign is added because the difference in distance is negative, and the difference in time is positive. According to K, the angle of reflection theta 13 can be computed as x3 minus x2 equals negative c times t3 minus t2 times cosine theta 13. We end up with the following set of independent equations. We can solve them to obtain the relation between the angle of reflection for observer K and K prime. From these equations, we can solve them to find the relation between difference in time and space as we have done before. To find the relation between the angle of reflections in frame K, which is theta 13, and K prime, which is theta 13 prime, we divide tangent theta 13 over tangent theta 13 prime. To find the relation between the angle of reflections in frame K, which is theta 13, and K prime, which is theta 13 prime, we substitute equation 23 into equation 24. We obtain the following equation. Dividing equation 25 over equation 16. We obtain the following equation. Since theta 12 prime equals theta 13 prime equals theta prime, this equation relates the angle of incidence theta 12 with the angle of reflection theta 13 in frame K. According to K, the light ray travels for a period of time which can be found by adding equation 22 to equation 14. We obtain the following equation. But according to K prime, the time intervals t2 minus t1 prime and t3 prime minus t2 prime are equal. Therefore, we will summarize the previous results. The angles of incidence and reflection are equal in frame K prime. This is the relation which relates the angle of incidence in frame K prime with the angle of incidence in frame K. This equation relates the angle of incidence theta 12 with the angle of reflection theta 13 in frame K.